share my screen here. All right, well, good morning to everyone. Let's just start with a few of our quick announcements here about things. Friday's lecture is on YouTube, so please let me know if you have any issues downloading it or even watching it. Office hours at the usual time, usual place, or after class at 11, and then in the afternoon at 4. And then the next homework assignment will be due this coming Friday, May 1st, 5 p.m. Pacific time. Okay. All right, so here's a recap from last Friday then. Let's let F be an algebraically closed field for the rest of the day, and let S here be the polynomial ring over F and n+1 variables. So you notice here that I am trying to label my variables so that I go from 1 through n, and then my last one here will be x0. So remember that projective n space is this collection of these equivalence classes where we'll say that two n+1 tuples are equivalent if there's a non-zero scalar where we can match them up in this way, right? So just a standard definition of projective n space. We also talked about homogeneous polynomials. So we'll say that a polynomial is homogeneous of degree e if we can do this here. So let's say if p looks like lambda q for some scalar lambda, then f of p should be lambda to the e times f of q for some exponent e. Right? So again, a homogeneous polynomial of degree e. And so once we do this, then we can let S sub e be the collection of homogeneous polynomials of degree e. Then we know that we have the following 5 properties. When e is equal to 0, the constant polynomials are just in correspondence with the elements from our field F. We also know that S of e is an S module, really, if you will, a two-sided S module. That just simply means that if F plus G, if F and G are homogeneous of degree E, then the sum is homogeneous of degree E. And if you pick any scalar A, then the product A times F is also homogeneous of degree E. Right, so we have these products here. Next, if you take two polynomials, maybe one homogeneous of degree I and another homogeneous of degree J, then the product is homogeneous of degree I plus J. So we just write that simply here by saying Si times Sj is contained in Si plus J. Right, so the degrees add when you multiply them, that's all. Next, in some sense, these sets are disjoint. So what I mean by that is if I have a polynomial that is homogeneous of degree I and homogeneous of degree J, then it just has to be the 0 polynomial. Right? There's no way that we can have a polynomial that's homogeneous of 2 different degrees unless it's the 0 polynomial. And putting all of this together, then we just simply say that we have here a graded module. So what I simply mean by that is every polynomial can be uniquely expressed as the sum of homogeneous polynomials. And so we just write this in this fancy way here, right, using this O plus. Today, what I'm going to focus on is the subset that we introduced last time, which is let's take a look at all the polynomials that are non-constant. So I put them all together. They form an ideal, and we call this the irrelevant ideal. So again, we take all homogeneous polynomials, but we stay away from the constant ones. So the polynomials of degree 1, degree 2, so on and so forth, then that will be this set here. Okay. All right. We then focused on homogeneous sets. So remember that a subset is called a homogeneous set if, first of all, it is the union here. So that is that if I look at the elements in T that are homogeneous of degree E, then I can union over all of those homogeneous of different degrees, and then that should recover back my whole set T. So roughly speaking, this says that everything in T is homogeneous of some degree. Right, so T is generated by homogeneous elements. We also want the intersection here to be either the empty set or the 0 ideal. So I just want to point out that there was a small typo in the homework set that was posted on Friday. It actually should say this, that the intersection here is contained in the zero ideal. So this intersection might be the empty set, but at least it's contained here in the zero ideal. So if we really have these two properties, then we call T a homogeneous set. And if you want to see more properties of this, I would just say look at the homework set number 9. We have a few properties about homogeneous sets. So for example, if you have a family of homogeneous sets, then the union of homogeneous sets is a homogeneous set. And roughly speaking, the product of homogeneous sets is a homogeneous set. So by product, what I mean is you just take the product here where each one of these lies inside of one of the homogeneous sets. So if there's maybe R homogeneous sets, and I just take the product, the first one from the first set, second one from the second set, so on and so forth. So that's what I mean here by saying the product of homogeneous sets. So again, these are two properties. And again, this here is part of homework set number 9. Finally, then, we talked about the Zariski topology. So I only mentioned this, but I do want to go over this again in a bit more detail. A subset of projective space is said to be Zariski open if there is a homogeneous set T where the complement of the Zariski open set is Zariski closed. So what does it simply mean by that is that it looks like the set of points where F here is 0 for all F and T. Right, so that's just what we mean here. So there were a couple of properties. First, the empty set and the whole space are Zariski open. Next, if you have an arbitrary family of Zariski open sets, then the union is Zariski open. And in fact, the union looks like the complement corresponding to this Zariski closed set, where we're here now, T is this homogeneous set. And if you have a finite collection, then this intersection here is also Zariski open, whereas the complement corresponding to this homogeneous set. So this just says that we have a topology. It says that the empty set's open, the whole space is open, arbitrary union is open, finite intersections are open. So whenever you have those 4 properties, then you say that you have a topology. So if you wanted to see more of why this is true, this is all written up in homework set number 9. Right. So here are the properties of what it means to be Zariski open, now in the projective sense. Okay. So last time we started to get into definitions of projective varieties. And what I want to do now is repeat what we did before, since I know that that was a lot of information and a lot of theorems. And then I want to spend the rest of the time today just going over example after example, right? Because this idea of projective varieties can be a really strange concept when you see it for the first time. So remember, in very simple terms, a projective variety is a subset that is irreducible, non-empty, and Zariski closed. Right? So that's just what a projective variety means. Now, we can try to make sense of this in more down-to-earth terms. Irreducible means you take a look here at this ideal. So this is the set of polynomials that vanish on all of x. So this here should be a homogeneous ideal. So that's what this says here. Right, so homogeneous just means that as long that I really want this to be generated by homogeneous elements. But that's kind of the philosophy. So that's what it means to be irreducible, that this here is a prime ideal, but it really should be a homogeneous prime ideal. Zariski closed simply means that x should be equal to the following set. So remember that once you have I of x, that's your prime ideal, you can look at the closure of this. So this is what I mean by z of I, the 0 sets of I. And then this here should just be equal to x again. So this is what it means to be Zariski closed now. So once we have all of this, now we can kind of write down a few definitions. The quotient here, our polynomial ring modulo this prime ideal, is what we'll call the homogeneous coordinate ring. And we know that this here is a homogeneous set because then we can just break it up in this way here, right? So the whole point here is that S is a graded ring, so S of X is a graded ring, right? So we have nice graded rings now that we're keeping track of. Next, we say that I is a homogeneous prime ideal whenever we can write our ideal in this way. So it's sort of like we can think of I as a graded ring, but the reality is we want to say that I is generated by homogeneous polynomials. So in the homework this week, you'll also see some properties of what does it mean to be a homogeneous prime ideal. And finally, we'll define the dimension of a projective variety as just the cruel dimension of our coordinate ring minus 1. And we'll see in just a little bit why we do this minus 1 trick here. Right, so again, this is what we mean by the dimension of a projective variety. Now we have a similar idea for quasi-projective varieties, and this is a non-empty subset which is Zariski open in some projective variety. So simply put, the complement here for some projective variety X should be the following 0 set. And this T here, of course, should be a homogeneous set. But we want it to be a homogeneous set that contains this prime ideal IX. Right, so again, it should contain this prime ideal IX. It should be a homogeneous set. And then we just want to make sure that really the homogeneous elements in the prime ideal sit inside of the homogeneous elements for our set T. Right, just so that everything kind of matches up in a very, very nice way. So again, these last two statements here say something about the homogeneous elements inside of T. So if we denote U bar here as the Zariski closure of our quasi-projective variety, then the dimension is just the dimension of this projective variety, U bar. Right, so just take a look at the cruel dimension of the homogeneous coordinate ring. Right. Now, I want to point out an important result that we're going to use over and over again for the next few days. Remember that we had this idea of the set S plus, which was the irrelevant ideal. So I want to point out that the irrelevant ideal is never contained in this prime ideal corresponding to any quasi-projective variety. So let me try to emphasize what's happening here, because again, we're going to use this over and over again. Well, let's try to do a proof by contradiction to understand what this means. The irrelevant ideal is the ideal generated by all of the homogeneous polynomials. So in particular, I know that I have the polynomial, let's say x1, the polynomial x2, the polynomial xn, the polynomial x0. Right? Remember that S is generated by these n+1 variables. So I can take those n+1 variables. They are homogeneous polynomials, so they generate S plus. Right? Again, all of the homogeneous polynomials. So in particular, they are generated by those n+1. Well, if the irrelevant ideal were contained in this prime ideal, then we actually know that U, our quasi-projective variety, would have to be contained in this intersection, right? Remember the S plus just is the union. So here we have this intersection. But really, if I just think about it, I want to take a look at the elements where each of the homogeneous polynomials vanishes. So in particular, let's take a look at the homogeneous polynomials corresponding to x1, x2, xn, and x0. Right, remember that our polynomial ring S is generated by these n+1 polynomials. So now I want to ask, what are the set of all points that vanish at all of the homogeneous polynomials? Well, if you really think about it, the only time where my points vanish everywhere is if the point is the origin. right? So again, I want to ask the question, what are the set of points where the x coordinate is 0, where the y coordinate is 0, where the z coordinate is 0, where all of the coordinates are 0? That has to be the 0 point, the origin. Here's the problem though. We're working inside a projective space. There is no origin. So there is no point where everything vanishes. So again, that's the whole idea of projective space, that we throw away the origin, so there is no point where all homogeneous polynomials vanish. So if the irrelevant ideal S plus were contained in this prime ideal, then U would have to be the empty set. But we said earlier, part of our definition is that a quasi-projective variety is non-empty. So I'm saying all of this to say, at the end of the day, the proposition here states that the irrelevant ideal S plus is never contained in IU. This is because there is no point where every single homogeneous polynomial vanishes. So this statement here, S plus is not contained in IU, is equivalent to saying that the origin 0, 0, 0 does not exist in projective space. Right? So again, the irrelevant ideal not being contained in this prime ideal is equivalent to saying that the origin is not a point in projective space. Now I'm going to come back and say more about this on Wednesday, but I wanted to introduce this now because this is something that we're going to be using over and over again. Right? So last time we went over this example of projective space, and I just want to remind you how this example goes. So let's let X be all of projective space. And as usual, let's let S here be the polynomial ring in n plus 1 variables. Now we know that the ideal generated by X is the 0 ideal, which is a prime ideal. So we see that it is homogeneous because then if I look at the intersection with any set of polynomials of degree E, then again, I get back this 0 ideal. And so then the union has to be the whole thing. So we see that IX now is a homogeneous prime ideal. It's a little bit silly here because it's just the 0 ideal, but it's still a homogeneous prime ideal. Next, we can look at the Zariski closure. So we have this homogeneous prime ideal, which is 0. So let me ask now, what are the set of polynomials that vanish, or sorry, what are the set of points that vanish everywhere for this polynomial? Well, if F is in an element of the 0 ideal, F is the 0 polynomial, and so then a 0 for all points. So the Zariski closure is just X again. Right, so it's not too surprising here. But now I'll put these both together to realize that projective space is a projective variety. Right, so that shouldn't be too surprising, it makes sense. Well, the homogeneous coordinate ring is just our polynomial ring S because we're dealing with the 0 ideal. So S here really is the coordinate ring of projective in space. So it kind of makes sense why we would use this notation here for S and why we even introduced S. Finally, we know that S here is generated by n plus 1 variables. So the cruel dimension of S is n plus 1. So I can then try to compute the dimension of X, which is the dimension of S minus 1. So that's n. That's why we take the minus 1. So I want to kind of correct things so that we kind of work in the right dimension. So we just proved now that projective in space is an n-dimensional projective variety, which it makes sense. That's exactly the reason why we're even using any of this notation. So again, projective in space is an n-dimensional projective variety. Right. So I'm going to spend the next 20 minutes or so just going over more and more examples to see if we can really make sense of what's happening here. And in fact, today I want to spend more time discussing projective curves. So we can write a definition that hopefully makes sense. A projective curve is nothing more than a projective variety that has dimension 1. Right? So hopefully that makes sense. A projective curve is just a projective variety with dimension 1. However, some weeks ago, we defined a projective curve in a different way. So if you remember towards the start of the course, we said that a projective curve is a subset in the following form. So here we were working inside of the projective plane, P2, and we said, let's take a look at the set of points where we want it to be the vanishing set for one polynomial. So we said fix one polynomial, this homogeneous of degree E, and then the zero set here should be a projective curve. So the question is, are these two definitions compatible? Well, let's see. To be a projective variety, we have to make sure of a couple of things. Number one, that it's irreducible, and number two, that it's Zariski closed. Well, since we have this generated by one polynomial, the ideal of x is generated by this one polynomial f. So I of x here is just generated by one polynomial. So we know what the ideal is. And actually, this has to be closed because if you just stare at the definitions, so ask yourself, what is z of I of x? Well, it's the set of points where this f here has to be 0. So it's just a little bit silly, but if you just kind of wind through the definitions and stare at it, by definition, this x is Zariski closed. Right? There's nothing more to worry about here. But I didn't say that this was irreducible. So here's the problem. When we naively define projective curve, we didn't focus on irreducibility. So here's where we have to be really careful. In order for our naive definition to be correct, we actually need I of x to be a prime ideal. So here's where I kind of cheated a little bit for the course. When I naively defined a projective curve back during the 3rd week or so of the course, I didn't say anything about irreducibility. All that I said was, we can write the set here, we're done. So now, in order for all of this to make sense, we actually need I of x to be a prime ideal. So what I'm going to try to do over the next 15 minutes or so is actually go through some of the examples we did earlier and focus on, do we really need to check that that I of x is a prime ideal? And I'm going to try to convince you that we actually already checked it. We're being a little bit sloppy about it. So let me make this last point here. If I of x were prime, then we actually do have a curve. So again, in order to check that our naive definition was correct, we need to check two things. That I of x is a prime ideal, that it's Zariski closed, but we already know that Zariski closed, so now we have to check that it has dimension 1. Right? Remember, we need projective variety with dimension 1. So if I of x were prime, then we know that Zariski closed, so that would give us that it's a projective variety. And now I claim that if it's prime, that actually forces it to have dimension 1. Okay, so.
Professor Royce, I have a question.
Sure.
So, like, does another version of this proposition holds for affine variety?
It does, right? In fact, part of the reason why I'm not actually saying that is that what I'm actually going to prove later is that an affine variety is actually a quasi-projective variety. So in a sense, once we prove everything for projective curves, it's actually going to hold automatically for affine curves.
Okay, thank you.
Yeah. Okay. All right. So first, I'm going to make an observation here that the height of this ideal has to be 1. So remember, right now I'm assuming that I is this ideal generated by f, and I will assume that I is prime. All right, so let's just make these two assumptions here. Well, first of all, the height we know is a non-negative integer, because remember that we have to have this chain of prime ideals. We know that the height is positive because this is not the 0 ideal. So remember that there was a homework problem, actually homework set number 8, where we're supposed to prove that the height is 0 if and only if it's the 0 ideal. So in this case, I know that the height has to be positive. Now, another thing is, I know what the dimension of our space is. So the dimension has to correspond to the dimension here. So the height is at most 2. Right, because again, here, I know that our space has dimension 2, so the height is at most 2. So the height here is positive, which means that it has to be at least 1. The height is at most 2 because we're inside of a 2-dimensional space. Well, this here now says that the height has to be strictly less than 2 because 2 things. Number 1, S here, of course, has dimension 2. Actually, S has dimension 3, but we're working with 3 minus 1. We also know that this here is not a maximal ideal because remember, we know what the maximal ideals of S look like. They are in this form. So again, this is what the maximal ideals of S look like. So the point is that if I of X were a maximal ideal, it would have to be generated by more than one polynomial. There's no way that this ideal, if it were maximal, can only be generated by one polynomial. So it is not a maximal ideal. Right? If it's not a maximal ideal, then of course it has to be strictly contained in a maximal ideal. But maximal ideals have height 2, so the height here has to be strictly less than 2. So again here, I of X is a prime ideal. We know that it's not the 0 ideal. We know that it is not a maximal ideal. So if you just do a counting argument, the height can't be 0, the height can't be 2, so the height has to be 1. Okay. Does that kind of make sense here, why the height has to be 1?
Yeah.
Okay. All right. So now we just do counting. So remember that there was a homework problem where I wanted you to show that the dimension of f of x, s of x, has to be this difference here. The dimension of the ring minus the height of the ideal. So the dimension here of s, we know is 3, because it's generated by these 3 variables, x1, s2, x0. Right, so I'll circle this here. So again, this here is s, it has dimension 3. I just proved that the height of this prime ideal is 1, so this means that the dimension has to be 2. But the dimension of x plus 1 is the dimension of s, of x, so the dimension of x here has to be 1. Right, so this here is just a matter of just counting. Okay, so here's what I want you to take away with on this slide. If I of X were a prime ideal, then we actually have a projective curve. That's all that this slide here says. If I of X were a prime ideal, then the definition matches what we expect. So our naive definition is correct. But we do have to check that I of X is a prime ideal for all of this to work. Okay. So what I'm going to do, yeah, question?
I do have a question. So is it like in the proof after the proposition, we are only dealing with the projective like P2 space?
That's right. That is exactly right. So here's P2 and then here's our S. That's right. So here what I'm saying is that this is to make sure that the definition we did way back like the 3rd week of class matches up with this new definition here.
Okay.
Right. So yeah, so the point is that our old definition, our naive definition matches the correct definition only if I of X is a prime ideal.
Okay, so it does not mean it's not a proof of the proposition.
Well, no, we did prove the proposition, but the point is that we have to check that I of X is the prime ideal.
Okay, yeah.
Right. Yeah, so if I of X is not a prime ideal, then our naive definition is totally wrong.
Mm-hmm.
Right, so that's kind of the whole point here, that we really have to check in all the cases that we're going to deal in just a minute, that I of X is a prime ideal. If I of X is prime, the definitions match, we're okay.
Okay.
Okay?
Cool. Thank you.
Okay, you're welcome. Okay, so let's start with our definition of lines and conic sections. So we just want to see, do our previous naive definitions match up with the new definition? So let's see here. Remember that we defined a line as a projective curve that corresponded to degree 1. Right, so E is equal to 1. So let's see here. Degree E is equal to 1 means that our polynomial here is this F. Now, if you really think about it, this is an irreducible polynomial because I cannot factor this polynomial. Right? If it's degree 1, I can't say that it's the product of two things, because if it were, then ask what's the homogeneous degree of that? If it's the product of two things, one of them has to be a constant. I can't say something of degree 1 is the product of something of degree I, something of degree j, where I plus j is 1. Right? So this here has to be irreducible. I cannot factor this any further. So this is an irreducible polynomial, but there's another way you can see this if you don't feel comfortable with that. Take a look at this ideal. And if I modded out my polynomial ring with this ideal, then I actually have a polynomial ring in two variables. So kind of the rough idea here is that if I have this linear polynomial, at least one of the coefficients here does not equal to 0. Let's say C0 does not equal to 0. So in some sense, I can solve for the other ones in terms of the first one. And so now I have a polynomial ring in two variables. This here is an integral domain. Therefore, I of x is a prime ideal. So it's a couple of different ways you can see it. One is you can say that this f here, I cannot factor it any further. Another one is to say here that the quotient is an integral domain, therefore I of x is a prime ideal. So a line really is a projective variety. It really is a projective curve. Okay. Now, remember that when we're dealing with fields of characteristic different from 2, a conic section corresponds to degree 2, but remember that we were really picky. We said we wanted non-singular curves. So again, a conic section corresponds to homogeneous of degree 2, but we want non-singular. So let's try to do the same things before. So let's ask the question, is our ideal a prime ideal? Well, if it were not prime, then let's take the arbitrary polynomial of degree 2. So here's a quadratic polynomial. Right? It looks something like this. And let's say maybe we could factor it. So let's say if we factor it, then it better be the product of two linear polynomials. Right? So again, if our ideal were not prime, I could factor this thing into the product of two linear polynomials. And now if you just kind of stare at the coefficients, then you get something like this here. Right, so again, this just says that the coefficients here, A1 through A6, have to be something in terms of the D's and the C's. Right, so this is assuming that we can factor it. However now, remember that here's how we define the discriminant of a conic section. And we said that this discriminant is non-zero if and only if it's non-singular. So to backtrack, here's what we're saying. If our ideal were not prime, then we could factor this homogeneous polynomial f, which means then we would have these coefficients here, a's, in terms of c's and d's. And if you plug in these a's into this delta of x, you would find that the delta of x is equal to 0. So again, if it's not prime, then the discriminant is 0. You just plug everything in, you just check that you get this here. However, we prove that if the curve is non-singular, then the discriminant is non-zero, proving that the polynomial is irreducible. So here's actually the crazy thing that we totally skimmed over weeks ago. If you're dealing with a conic section, it must be an irreducible variety. Because if it's a conic section, then the discriminant does not equal to 0, and therefore it cannot factor. Because if it could, then the discriminant here would have to be 0. So we completely skimmed over this. But this is part of the reason why I skimmed over it, is that non-singularity actually implies that things cannot factor. Right? So we actually are dealing with the prime ideal. So we are dealing with the curve. Okay, any questions here on these examples, lines and conic sections? Okay, all right, let's keep going. What about elliptic curves? So now let's assume that the characteristic is different from 2 and 3. So we said that an elliptic curve is a non-singular curve of degree 3. So now we did a lot of work to prove that if we have an elliptic curve, then its discriminant is non-zero. And remember that we did this weird work to prove that we can take any homogeneous cubic and we can place it here in short Weierstrass form. So there was a lot of work that we did behind the scenes here. There was a lot of moving around coefficients and what have you. But the point is that if the discriminant is non-zero, then we know that the curve is non-singular, and we can place the curve here in short Weierstrass form. Right? There was a lot of work that we did to get it to this point. Now, what I'd like to do is convince you that this homogeneous cubic has to be irreducible. So let's say, what if it were not irreducible? Well, then this means that it would have to be the product of maybe a linear and then some quadratic. The quadratic itself might also factor into other pieces, but I don't care. Let's just say for the moment, it might be at least something of degree 1 times something of degree 2. So we're going to do exactly the same trick as before. So assuming it's reducible, we can factor it as a linear times a quadratic. So that means that we're going to have conditions on these coefficients, the C's and the D's. It turns out that we will have 10 equations involving these coefficients. So here's the first 9, right? And those would be these equations here. Well, the first 5 here actually force these coefficients to be 0. Right, so that's the first 5. And then the latter 4, they actually force these here to be specific values, where the E here is just going to be a root of this degree 3 polynomial. So I would say don't worry about the latter 4. I care to talk about the first 5 over here, because they force these 4 to be 0. But what I haven't said is that there is a 10th equation. The final equation is this. Now, I claim that these 6 equations that I'm circling are not compatible. So again, if the first 5 hold, then that would force these 4 coefficients here to be 0. But you'll see now that if C5 and D3 are 0, then I would get 0 equals 1. So again, these 5 and then this 6th one are not compatible. So there is no way that I can factor this homogeneous cubic into other factors. So that means that this ideal here must be prime. So again, this is another example where we see that as long as the discriminant is not equal to 0, then we cannot factor things. Right, because remember that if the discriminant is not equal to 0, I can place this here in short Weierstrass form, and I just proved that short Weierstrass form cannot be factored because I can't find solutions to all of these 10 equations. So what I wanted to emphasize here is non-singularity for degree 2 and degree 3 actually implies that we have to have a curve. So things here are irreducible, that we actually have a prime ideal. Right. Okay, questions so far? Okay, so let's try to finish things off now by going to degree 4. So this is the quartic curves. And here I want to try to combine everything that we've been doing all into one place. So let's consider now this quartic polynomial, right? So our f of x here. And let's denote the following set x. So x here is going to be the set of solutions now for these 2 polynomials. Remember that we call this here a quadric intersection, We can also write this in terms of like the affine point of the curve, as long as we throw in these 2 points at infinity. But the point is that now you'll see we're working with something sitting inside of P3. Now, intuitively, we expect this to be a curve for the following reason. Here we have really 3 variables. You can really say it's a 3-dimensional space, so n is equal to 3. But now we have 2 equations. So m is equal to 2. And in this case, n minus m, 3 minus 2 is 1. And remember that this is how we defined what does it mean to be a curve, even in the affine sense. So the number of variables minus the number of equations should be 1. N minus m is 1. So we do actually want to check that everything does work out. So again, here we just have our set corresponding to these 2 quadratic polynomials. And remember that we proved that our x is a non-singular variety if and only if f of x has distinct roots, if and only if this discriminant here is non-zero, where we write everything here in terms of a and b in this way. So remember that we did a lot of work proving that here it's non-singular if and only if this discriminant is non-zero. So I'm going to use this now to try to convince you that the ideal generated by these 2 has to be prime. Okay. So now we just can't simply say, well, worry about whether or not these factor, because that isn't quite right. Now we have more than one polynomial. So we have to be really, really careful as to what we're doing. So hopefully this discriminant kind of motivates, maybe we should reduce to the previous case of elliptic curves and go that way. Well, that's exactly what we're going to do. So we have this a and b, so let's denote y as this elliptic curve here. And let's observe that we actually have a map from our quartic curve, our quadratic intersection, to the elliptic curve that's defined in this way. So we've actually been doing these formulas over and over again throughout the course here, but I wanted to point everything in one place to say that if we start with our quadratic intersection x, and if I write down this elliptic curve y, then here's a map that goes from points on x to points on y. All right, so this here is a well-defined map. If you want to know what is e here is just the root of our quartic, our f of x, our degree 4 polynomial. So using this, we actually find a ring homomorphism. Quite literally, you take a polynomial in the y's, you make this substitution here, and now you have a polynomial in the x's. Right? Literally, that's all that you do. You just do a substitution. Whenever you see anything with the y's, substitute, you get back something in terms of x's. So now you have a ring homomorphism. Notice how the order here gets swapped. So phi here was a mapping that went from x to y. Now here, phi star is a mapping that goes from f of the y's to f of the x's. So the order gets reversed here. You can actually prove that this actually induces an isomorphism of homogeneous coordinate rings. So it's a little bit of work, but you can actually prove this. So this means, on the one hand, s of x, which we write for our quadratic intersection, should be isomorphic to s of y, which we get from the elliptic curve. So again, this map here induces an isomorphism. So now we're actually done because we realize that since we have an elliptic curve, I of y is a prime ideal. We just proved that. But this map here gives an isomorphism. So if s of y is an integral domain, then s of x is an integral domain. And therefore, I of x, the ideal generated by f1 and f2, must be a prime ideal, a homogeneous prime ideal. So the cool thing is that we just reduced everything back to elliptic curves. But here, what I want to emphasize is that there's 2 things I want you to take home. One is we found a map between varieties, and that reverses the order here for the rings. But this map of varieties was nice enough that that actually induces an isomorphism for the coordinate rings. So we're going to play around with this a bit more and see this a bit later. Okay, so any questions on these examples here? Okay. All right, well, let's call it a day then. So then next time, I want to say a bit more about how the affine varieties and projective varieties are all related. And I want to try to put everything together into one coherent theory. All right, so you all have a good rest of the day and see you on Wednesday then.
Thank you, Professor.
Okay, thanks. All right, take care.